Okay, good afternoon. Um, let's get started with the material for this afternoon. Before we get started, I passed the assignment, the graded assignment. So make sure that if you got something wrong, that you go check your solution. And as always, if you still have questions, we can talk during my office hours or after class. Um, Then the next thing that I wanted to mention is that you make sure that even though you're working, you can collaborate, right? But make sure that you submit your own work. Could be by hand, it doesn't have to be typed. But the only way that I know that you're working and that you are actually making progress in the class material is by showing your own work on the assignments. So I don't have too many students in this class, so for me, it will be very easy to identify when that's not happening. Then there's some of you asked me about the variables, the software defined variables for Arena. So if you go to the modules for today, I have posted a PDF file with those definitions. So one of the items in the module for today will have the list of variables for Arena, including TNOW and those associated with the resources, the counters, and so on. That being said, today we are going into the modeling part of this class, and we're going to start adding some logic that is currently it's going to be used most of the time when you're dealing with manufacturing lines in which you have an operator taking care of some of the activities, specifically with some of the machines. An operator that will have interaction, let's say setting up a machine or picking up some of the parts that are completed in order for the process to continue. So today we're going to talk about how to implement that type of logic in Arena. And will involve some of the blocks that we already learned in our first two labs for Arena in this class. And specifically, we're going to be looking at different ways of using these seize, release, delay blocks. So now it's not just going to be a machine waiting for a part to arrive and then process and then release the machine. Now we're going to have a second resource interacting with the machine, and you need to make sure when to call one of the resources for setup and then release that resource, process with the machine, then call the resource again if you need to remove some of the parts, and then continue the process. So that's the idea for today's lab. And we are also going to be collecting some of the statistics that we collected last time. So just to give you some additional practice for how to set up that information into your models. And I think that's basically what we are going to be doing this afternoon. So today's lab is going to be more into setting up that logic. How do you set up the logic for those interactions? So if you look at the slides for today, there are similar to what we discussed last time. So I got a question about how do you know an attribute, why specifically the arrival time is considered an attribute. So again, attributes are properties of an entity that are not changing. So once you assign that property to that entity, it's like bringing some information to that container, and that container, which is the entity, is going to be moving through the system until you discard that entity. And anytime you need some information about that entity, you can call that container and grab the information that you need. So for our previous activity, we're trying to collect the cycle time, the timing system. So for us to be able to compute that cycle time, we need to have some information, right? And that information was stored in that container, and that information is stored in as an attribute, specifically the arrival time. So you bring that container, you open the container, you take the information that you need, and then you can compute the cycle time for your entity. And then many of our models, you will have 100, 200 entities going into the system. So yeah, every container will have individual information for each one of those entities. Is that clear? So things like color, size, arrival time, costs. At some point, we're going to be talking about processing costs, part types. All those are considered attributes. And they will be assigned to each entity if needed. Okay, so, and here's how that is performed. We also talk about decisions. So how to implement those decisions using the branch block. So I think I saw some of the solutions already for last lab, and I saw some of you already working with the branch blocks. So decision making, that's what you need. There's two different type of decisions that you can make based on an attribute, like in this case, in which you can use an if statement, or you can use probabilities. Like with this probability, you're going to send through this branch. With this other probability, you will send through this other branch. Statistics, we counted already some of the parts completed in the first two labs, actually. We did that. What was new in the previous lab is now that we are generating this output report, right? So now we need to make sure that we set up the report by computing these average statistics for tallies, for these stats, and for counters. So we define those software-defined functions that are allowing you to compute those statistics, and we implemented those in the output elements. So we discussed the differences between these three: the count, the tally, and the time average statistics. We discussed the counter. It's just very simple. You're counting entities at any point in the model, any point in the simulation. The tally is it's a container that is saving information about all the entities that are going through that block. And at the end, you compute some statistics based on the information inside that container. And then we have the time average statistics that are for those statistics that are changing during the duration of the simulation. So these are things like the utilization is something that is going to be varying through the simulation time. Also, things like the number of entities inside the system, you're going to have arrivals, departures. So at any time, those numbers are going to be changing. So we use the time average statistics just to get an idea of what is the average status of those performance metrics. So time average statistic is a weighted average. For example, the working process weighted by the proportion of time during the run that the system had that specific value. And then we use the DAVG to obtain the average for the output report. The tallies, we talk about that, the sets, and we implemented the set for the model that we built last week. What is new for today? We talk about these stats already. So now we talk about how to compute the average for the output report. When we talk about utilization, today we're adding another D-stat, which is the average numbers of parts in a queue, right? And that is another time average statistic, how many people you have in queue on average during the simulation time. So now we're going to be looking at the queue name, and we are going to use this MQ defined variable from Arena to compute that average, right? So let's think about, anywhere you go, you most likely are finding a queue, specifically if you go for lunch. If you go for, I don't know, you go to I-35, you will find at 5 o'clock a long line of cars, right? So we know those lines are changing depending on the time of the day. So we are keeping track of that information. And at the end, we want to know, okay, on average, what will be the size of the queue during the time that we are observing this system. So we can use that NQ to compute the average number of parts, in this case, in the queue. This is very relevant, for example, in service systems, like if you're analyzing emergency rooms in a hospital, knowing how many people on average are waiting in the waiting room is important. If you're dealing with airport security, like security checkpoints, you want to know how many people are waiting, so you know how many lanes you can open at any time to make sure that the passengers are flowing, but you're not impacting the security of the airport. So specifically in service systems, this is very relevant. Restaurant services, same thing. Most people, when they go to a restaurant and they tell them, we have these many people waiting before you, they most likely are going to leave. So you want to know what's that number that will make a customer leave before or wait for service, right? So if you tell them there's 2 parties before you, they might stay. You tell them you're 5, they just go to another restaurant. So that's why it's important. Okay, we talk about statistic, replications, how to use the output report. So today we're gonna do that again for the example that we're gonna cover in class. And this is the situation that I was referring to early today. We still have the same environment in which we have 2 resources, in this case, 2 drills. But today we don't have part types. I don't want to focus on the attributes, specifically the part type attribute. I want to focus more on the logic that we are going to be implementing today. So that's why I'm simplifying the exercise a little bit. So no part type, 2 resources, but these are identical resources because they have the same processing time. So we don't have separate queues for them. We can use any of the 2 once the part arrives to the service station. They will pick the one that is available. And then once the parts are completed, they're gone. But there's an additional element here, which is there's a single operator who must set up each part on the machines and remove each part from the machines. So you have to perform these 2 activities in order for the process to continue. So in this case, you have a single operator, 2 machines. So you know this person is going to be moving from one machine to the other, perform the setup, and also for the removals. Both the setup and removal times are distributed according to a uniform distribution. So the setup time goes from a uniform to 4, and the removal is less time, 1, 2, uniform 1, 2, and this is in minutes. So the questions we want to answer is how many parts are processed in 8 hours? What is the average number of parts in the queue? And what is the average utilization of the machines? Okay, so before we get into the actual implementation, I want to spend some time just working on the logic. Right, so let's talk about that. Okay, so we had 2 resources, right? So drill 1, drill 2. We have parts arriving, so they're going to choose the first drill that is available, and then after that, they're disposed. But we have an additional constraint now is not just two resources, right? We have an operator. It's just one operator, but this is an additional resource. So it has to be modeled as a resource as well. And we want to set up a logic in which this operator is going to be interacting with these two machines. Again, in this case, we are assuming that the machines are identical. So we can set up only a single logic line or sequence of blocks for both machines, and then just change the capacity in the elements. So we can start by setting up that logic in which we have a seize, delay, and release. And this is for, let's say, red. Is for the machines. Okay, so I'm gonna change the colors here because I want to start adding some logic for the operator. Okay, so so when you have these two machines, let's say a part is arriving from your point of view, say this is a part, modeling those parts using these squares. So let's say a part arrives to the queue. So let me put that queue here. So what would be the first thing that you would do in terms of seizing resources? Yes, you will see the operator. That's correct. But is that the only thing that you will need available? You will need to have available to set up the part. I know you need the operator, and you need a machine, right? So essentially, for you to be able to set up a part, you need both resources available, right? So this seize block right here will be doing a seize not only for, let's call this, this is confusing, calling them. So I'm gonna still seize the drill and also the operator. Okay, so that's my first seize. I'm calling this machine. I'm also calling the operator. If both of them are available, I will set up the part. So what needs to happen next? That's correct. So next, I need to come here and I need to date. This for this case was the uniform 2-4, right? Which is the time it takes for you to do the setup. What happens next? Yes, so next, since we are done with the operator, I can release the operator. Right, so I can do that here. So I seize both. I do the setup. I release the operator, but I'm still holding machine, right? I need to do the processing now. So now I'm going to do the delay for the machine. Okay, so that delay is triangular or something, right? 2.2. And this is for machine. So I'm done with the processing. What happened next? You got to do what? You got to call the operator again, right? So let's do the same thing. I'm gonna go here. Let's see. That will be the best way to do this. Here. I'm gonna call cease. Cease the operator. And also now that once the operator becomes available, I need to do the removal, right? So I need to lay this again. So this is a uniform 1, 2. And then go back here. What's the last part? I need to do the release of both, right? The trail. Okay. So that's the logic right there. That's how you set up this interaction. You do the seize of both of them. You need to make sure that both of them are available. If that's the case, then you hold those two resources and you perform the setup, which is following this delay of a uniform distribution to 4. Once the setup is completed, I release the operator, but I still hold the machine. I go to the delay for the machine. I do the processing. Now, after the processing is completed, I need to hold and wait until the operator becomes available again. So I'm calling this operator. Once the operator becomes available, he comes to do the setup, which takes a uniform 1, 2 in terms of processing time. And then at the end, the process is completed. At that point, I release the machine, I release the operator for the next part. Questions? Looks simple, right? Yes.
What if we have multiple operators?
Multiple operators, if they are identical, right? You can just increase the capacity instead of 1 to 2. Yes, in the resources. If they're different in terms of the processing time, then it becomes a little bit more difficult. For that, you're gonna have, and I'm gonna teach you that in class. You're gonna have to create a set of resources, okay? And then the C's, instead of calling an operator specifically, is gonna call the set, and it's gonna find the one that is available.
Like we have said,
We did this.
that is like for output. Like
We did a set for the statistics, the tallies, right? We can also create a set for resources. But we are not there yet, but that's a very good question. So in the case in which you have resources that are identical, you can just change the capacity. In the case that you have resources that are the same in terms of the tasks that they perform, but they have different processing times, we can set up a resource set and then seize based on that set. Any other question? Good. So let's implement this in Arena. So all of you brought your computers. That's good. Yeah, this time I didn't bring the laptop card, so I was under the assumption that everybody was gonna bring their own equipment. Okay. So
There isn't a queue in between the operator and the machine.
the operator and the machine. So the queue is set up in front of the Cs, right? For the at the time of arrival. So that queue is gonna hold any entity there until both resources become available. So that's where the queue is. Then after the processing time of the machine, we call the Cs, and there's no queue in front of that one. The Cs block is not needed because that machine is not going to become available. It's being held by the part. So it's not like you're going to allow any part to come into the machine until the machine becomes available. Right.
So just for clarification,
Mm-hmm.
whenever you have an entity coming into the operator and the operator is seizing the entity, the operator can't be doing anything else except for seizing the entity as much as the entity can't be doing anything else either, right?
Yeah, so for the operator to perform an activity, any activity, it has to complete the activity on hand before. Yes.
Awesome.
Yes. Any other question? Okay, so we're gonna start by just saving the model. Okay, so save your model and then let's go to the project bar and find the templates, the blocks and the elements. And I know you guys at this point should be familiar with the split that I do for the experimental frame and the model, but still like to make it um, readable here. So model. Okay, so I will start by setting up my experimental frame. So we know we need a queue. So I'm gonna start by adding the queues. We also need to define our resources. So I'm gonna add the resources here. What are the statistics that we need to collect? Parts process, average number of parts in the queue, and the average utilization. So how many parts are processed? This is the counter. And then for the number of parts in queue, we don't need to define anything that's associated with the queue. Same thing for the utilization of the machines. So I think at this point we're good. We need to add the counters. So let's start. Bless you. And for the time average statistics, we need to define the dstats for the output report. So I will add that as well. And then finally, the output. So I think those are the ones that we'll be needing. We can add more later if we find that we need something else. But for now, I think that's all we need. So let's define the names, starting with the queue. So I'm gonna call this just process queue. Okay, so this is the queue that is gonna be in front of the manufacturing line. First in, first out. And then we have two type of resources. Let's start with the drills. So I'm gonna call these drills. And since we have two, but they are identical, we can just change the capacity from 1 to 2 here. So we're gonna have 2 drills. So I'm gonna put here 2. And remember, this is because they are identical. If they were different, to build this type of logic, we need to define a resource set as well. Okay, so
Different in terms of what?
processing times. Yes. So we will get there. But for now, I'm more interested for you to understand how to set up this interaction between operators and machines. Okay, so we have the drills, and then we have another resource. So you see here, you already have the drills. If you want the other resource to show up in this list above the drills, then you keep the blue line there. If you want the operator to show up after the drills, then you have to come to the end of the list. It doesn't make a difference. It's just preference. So I'll put operator here. And the capacity is 1. Then we have how do we call this? The parts process. So this is gonna count parts processing. Okay, so this is my counter. And then I have 2 these stats, one for the utilization. Okay, so I'm gonna add here our expression here for the utilization. If you remember, we need to use the NR. and then the name of the resource, which is drills, because we want the utilization of the machines, right? Average utilization of the machines. So we have NR drills, and if you remember from our discussion, we need to give this stat a name. So I'm gonna call this machine utilization. Wanna call it, to be consistent, drill utilization or drills utilization. Questions? No. Okay, so we have that one, and then the other one, which is also a time average statistic, is the average number of parts in Q. So as explained today, instead of using the NR, we're gonna use the NQ. And the name of the queue is process queue. So I'm also need to define a name here. It's gonna be long. So number in process queue. You don't have to be, I mean, for me, it's easier to write this long thing because then I'll remember what I was trying to do with this. But if you want to use something short, that'll be okay too, as long as at the end you have the right report.
Can you use underscore in this?
Underscore, I think Arena doesn't allow underscore. Let me see. We will need to run it. I think it gives you some errors. That might be fixed, but we can try.
Be appropriate to name the entities like work in progress? Or would that be like a misuse of the
So working process is not necessarily only the entities that are in queue.
Right.
It might be just standing somewhere else. So again, the naming is up to the decision maker, the person, the modeler. As long as you get the right report at the end, it doesn't really matter, okay? But when we define the working process, in general, we are referring not only to the entities in queue, but it will be everything that is inside the facility. Good, so we got the these stats. And then for the outputs, we will have to refer back to that. So for the output, we have the counter, which is NC. And what was the name? The counter parts process. And then the name is the average parts process. Got it? Okay, so I'm gonna click here because I need to go back and copy the names. So this is drills utilization. So I'm gonna copy that name and I'm gonna go here and I'm gonna add a DAVG and then that name. And this will be the average drills utilization. Got it? And we have to do the same thing for the Q. So I need to come here, copy this name. And then create a DAVG with that name. And this is the average number in process queue. Got it? Good. So let's save this. Make sure that you save your progress to this point. We have set up the experimental frame. Now we can use that information for our model. So we will start with the create block. And let's go back here. It is Expo 4.4. So my interval, I'm gonna go here to build expression, Expo with the mean 4.4. So I have an exponential with the mean of 4.4 minutes in my interval. That's the arrival process. In this particular lab, we are not defining any attributes. They are not needed. So we go straight to RQ. I'm going to connect these two. For the queue, we just need to find the name that we defined, which is the process queue, and assign that name to this block. So we got the queue. And then we proceed with the logic that we discussed, right? So first thing that we want to do is to cease both. So in this case, that order matters. If you seize the machine first and then the operator, or the operator first and then the machine, you'll see that you will get a small difference. It's not gonna be something that is gonna change your recommendations, but it will be a difference, a small difference with the performance. So this will depend mostly on how you see it, right? From my point of view, I will only, well, you gotta seize them at some point. You will not call the operator if the machine is not available, right? So one machine has to be available before the operator makes a decision in terms of I'm going to go and set up this machine, right? It's not like the operator is gonna go get a part and wait for the machine to become available, right? So I'll put the machine first. I need to make sure that the machine is available so the operator can see and say, okay, I need to go set up. So I'll put the machine. So the drills. And then, as I said, if you leave it like this, it's gonna put the operator first. So I don't want that. I want the operator to be called second. So drills operator.
So the drills are grabbing it first.
Drill have to be available before the operator is called.
Right, the priority one is what,
Say that again?
the dialog box, there's a priority is one. Yeah, this priority, yeah.
Oh, so that's a good question. So there'll be situations in which you have multiple seize blocks calling the same resource. Like in this case, you're seizing multiple drills. But let's say you have 3 queues that are separate and they're all calling the same resource. You can assign a priority for the resource to get assigned to one of these 3 queues. Right, so you put this one first. This C has a priority 1, this one has a priority 2, and this one has a priority 3. It will assign to the first, the one with the 1 first. Good question. So yeah, we will also work with that at some point this semester.
If we have like defined operator for defined machine, then in that case, should we use 2 for operator on like now we're using the 1. Number of units.
So this priority is more in terms of the entity priority. So which entity will have priority in terms of getting the resources? It's like you are a patient in the emergency room. You comes with a headache, and the other one comes with the blood in their hands, right? So which one will have priority? The person with the blood, right? So that's what this is trying to do. So you have 2 different type of requests. Let's say 2 different queues, or 2 different, not queues, but 2 different create logics, different entities, and then they're calling the same doctor. Doctor will go first to the one that has the highest priority. Yes. Good questions. So we got the C's for both. And then we got the delay for the setup. So this duration is, yes, uniform 2-4. So minimum value 2, maximum value 4. So you delay and then you release the operator. Right, so let's find the release. And then here you just release the operator. So this completes the setup portion. So this is the setup. So
So operator or the. We pass, see by the operator.
here you see it's both. You perform the setup and you release the operator only. You keep the machine. All right, so let's see. Let's try to build the box around it It's not that simple. Anyway, so we got the setup here. And then after that, after the setup is completed, we go to the delay for the machine. Right, so that delay follows a triangular 3.2, 4.2. Okay, so we got the processing now. That the processing is completed. I'm gonna call the operator again. So I got find the C's. And here we just need to seize the operator. Say that again. This. So now, once the operator is seized, we need to delay for the removal of the part. So let's find the delay. And this delay also follows a uniform. One, two. And now we get the same decision in terms of what is going to be released first. So what do you think? First what?
Oh, which one comes first?
Yes.
The machine comes first?
Machine operator is working on the removal, right? So once the part is removed, that machine is available, right? So it seems to me that the machine is gonna be available first, and the operator needs to set up the part. So from that perspective, I'll put the machine first, and then the operator. So next, we need to use the count block to count how many parts are processed. And from there, we can just dispose. Okay, and I'm gonna save. And I want to do a quick check for my model. You should do the same thing after saving. Let me know if you have any problems with your model. No? Good.
It can the rate of utilization of the drills be more than one because it's counting up as a double resource.
Yeah, and we're gonna fix that. Yeah, that was one of the things that I want to show you. Because since you're counting the information for both, you gotta split them up. Yeah. We actually look at the average. So you have two, we have to divide it by two. That's good. So let's set up We are trying to run this for how long? 8 hours. So let's first set up the report. So we're going to use the Siman output report and then move to project parameters. So this is example 3. And then you should uncheck this if you just want to see the statistics that you are specifically collecting for this exercise. If you're gonna get more information, you can just leave those marks there, but it creates some problems in terms of trying to identify what's the information and where is it located. And then for the replication length, we are gonna run this for 8 hours. Our base time units are minutes. And then let's do 10 replications or 10 different experiments. Okay, so let's run it. Yeah, so this is what I got. Let me know if you got something different. You got the same thing? So, yeah, if you look at the average drills utilization, that number is above 1, which is more than 100%, which is not correct, right? We want to make sure that the utilization is always stated in a bound from 0 to 100. In this case, from 0 to 1. And the reason that we're getting 1.92 is because we had 2 drills instead of 1. So we can fix that by doing a small change in our computation here. For the outputs, go to drill utilization, and we can divide this by 2. That DAVG drill utilization, divide that number by 2 because we have 2 machines. We are looking at the average utilization for both. Let's see how that works. And something else that I wanted to show you. See, it takes some time to run this. There's an option here that says batch run, no animation. If you check that box here and you run your model, it should run quickly. So you see now for the average drill utilization, you are 90.96. So it means like you're getting very high utilization for both of your drills. Average number in process queue, you got about 7 parts waiting to be processed. So it seems like you still have some, I mean, the utilization is telling you that you're running this process. Your machines are busy most of the time. You have some parts typically waiting, about a little bit more than 7 parts always waiting. And you are only processing about 100 parts per day. So things that you can do to improve, let's say, what would you, based on these numbers, if you would like to increase your throughput, what type of things you can do? Let's try that. So how do you go about that here in the model? You go to resources, right? You change that capacity to 3. And do you think the operator is going to create some bottleneck? Let's see how that operator is making problem here. Yeah, so the drills seems like they're not idle at all. So the operator's is doing a good job in terms of setting up the parts and removing the parts. But I wonder if we have another machine, if that will be the case. Yes. So you see now, utilization went down a little bit. Number of parts in queue also went down, so they're not waiting as much. But the average number of parts processed also went a little down, right? This could mean several things. Like by the time this is done, maybe there's 3 parts still being processed that the operator might not be able to get. But it seems like the operator is becoming the bottleneck in these exercise now. You added more machines, still not have enough people to handle these three machines. So want to try something else instead of increasing the number of machines. Let's change that back to 2. You know, the utilization is high. What if we find a way to make this machine faster? Like we do some type of setup and processing time might, let's say, go from that maximum time is the only thing that I want to change. So let's do 4.8. And maybe we're performing better maintenance or see if that's going to make any changes. It didn't change much, right? Like one more part maybe. Yeah, it didn't make much change. The utilization went down a little bit. So it seems like the problem is a little bit more complicated than we think, even though it looks simple, right? We still have, I mean, about 8 parts that are waiting. So there's opportunities for us to get more parts, I guess. But it would have to be a combination of maybe adding another operator and adding more capacity to our machines, which might not be cost effective, right? Because maybe you're adding these other 2, or maybe adding another operator will cost you more than the additional parts that you might be able to process. So as you can see, these are the type of things that you can start doing with your model. You start asking questions, the model is validated. Things that you might think, oh, I can just improve this system by throwing another machine or making the machine faster. If you don't have the simulation and you just go with your gut, you might spend a lot of money and then no see any improvement. So that's why getting to build these models are important, because before you make those decisions that might be expensive. Questions?
I wanted to, this is kind of like a one process, but it's not like the one process,
Mhm.
but if we had a more clearly like two processes. Would I be using the NQ to, know what are happening to my queues, throughout the process?
Oh, so your question is in terms of, let's say you have a second station? Yeah, you will need to add another queue if you have a second station.
With a completely separate queue?
Yes,
Okay.
yes. So in that case, you can track. Yeah. And the good thing is in class, not only in when the analytical part comes, and we will talk about that. We will talk about, let's say you have two stations and they have different processing times and they might have different variability as well. So how do you know if you want to improve your process, which one of the stations is the problematic? How to identify the one that is problematic? And the interesting thing is like most of the time, our intuition and the numbers are not connecting. Like you will think, this is the problem, but when you look at the math, it's actually, especially when we deal with this uncertainty and variability, math can tell you, based on what you have in terms of number, this is the actual problem. So we'll look into that as well. Any other questions? Not then there's another assignment for modeling. Make sure that you start working on that. If you have questions, again, I have office hours on Thursdays. I have office hours today as well at 3:30. So you can stop by if you have questions. And Thursday and Mondays, even though I don't have official office hours before the class, but I'm typically in my office after lunch. So if you have questions before the class, you can also stop by and we can clarify any questions at that point. Okay, if not, then I'll stop here and I'll see you Wednesday. Thank you.